Alright guys, we're going to carry on with chapter 14.4, power and efficiency. Okay, so it says the motor M, we're going to look at this example. The motor M of the hoist, right, there's the motor, lifts a 35 kilogram crate, so that the acceleration at point P is a point right outside the motor. Right? So the acceleration of P is 1.2 meters per second squared. Determine the power that must be supplied to the motor. Okay, take note of this. Supplied to the motor at the instant that P, the point P, has a velocity of 0.6 meters per second. Okay. So the question is, I've just rewritten this or redrawn this so that we're looking at this face on. We have a point P here, which is right outside the motor. There's the motor, okay? So if you recall, mechanical efficiency is P out over P in, all right? So it is how much power does a motor or an engine output in relation to how much power is put into the motor. So for example, we have a motor here. You can it has some sort of energy source. One way is to just plug it into the wall, okay? And there's power coming in. So this power that's coming in is what they're saying here. How much power is supplied to the motor? So the power supplied to the motor is power in, and power supplied by the motor is power out. So please take note. Supplied by, supplied to. All right? Okay. So we're looking for this P in. Can you think of a way that we're going to do this before we do any calculations? Well, we've got this equation here. Mechanical efficiency is the power out divided by power in. We've got the mechanical efficiency. This is 0.85. Okay? And we're looking for P in. So it seems that what we're trying to do is we are trying to find P out. Now P out is what? It is the power that the motor is delivering right there at point P, right outside, so to speak, the motor at point P. This is where the motor is delivering power. It is supplying power. Okay? So what is power? Power is F dot V. Okay? It's the dot product between the force and the velocity. So what do these now refer to? So the output power, okay, of the motor is then the force here at point P, which will then be given by a tension, right, the tension in the cable, and the velocity of point P. That's what we're looking for. We're looking for the tension in this cable at point P, multiplying it by the velocity at point P. And we've already got the velocity at point P, it's 0.6. But now, so the question is, we're looking for this tension. All right? So how would we find the tension then in this cable? We know we would say sum of the forces in the Y is mass times acceleration of the crate, that's C. All right? And one thing I want you to take note of, which is quite important, is that what we'll see later on, because we're having pulleys here, we will also carry out pulley equations, right? The absolute dependent equations. And it matters whether you take down as positive or up as positive. The point is, all I'm trying to say is that when you carry out your equation of motion here, right, you must have the same direction as when you carry out your pulley equations later on. They must have the same direction. Okay, otherwise you're going to run into trouble. Okay, so we're choosing down as positive for our acceleration and our forces. The reason why is because later on, when we carry out the pulley equations, we're also going to choose down as positive. And they must be the same. Okay, So now, what are the forces then acting on the mass of C, this mass over here? We've got weight acting down, right? If we draw a free body diagram, we've got weight, and we've got 2 times tension, okay? Because we've got the tension in the cables. Weight minus 2 times tension, because tension is up, and it's in the negative direction, is equal to mass times the acceleration of C. So what we'll find is, we can find this, it's mg minus 2t, so we still don't know what is t, but we do know what's mg, and we know what the mass is, it's 35, but we do not know. So the unknowns here, the unknowns that we still have are t and the acceleration of the crate. We're looking for t, but we have 2 unknowns. So we can park this guy over there. How do we find the acceleration of the crate? This is where we have our pulley equations, okay, for the lack of a better word. So we set up our datum, right? That is SC. There's another datum there, and that is SP. So we have 2 times SC plus SP is the total length, right? So if we differentiate this twice, we get 2 times AC is minus the acceleration of P. Do we have the acceleration of P? Yes. The acceleration of P is 1.2 meters per second, so the acceleration of C is minus a half times 1.2 equals minus 0.6 meters per second squared. Okay, so now we've got acceleration of C minus 0.6, and there is the equation. We put our acceleration in and we calculate the tension. Great. Now we've got our tension and we've got the velocity at P. We can calculate our power that is being supplied by the motor. Power out. Tension times velocity, and there we got it. Power is 109.3 watts. But we haven't solved the question yet. The question is, how much power needs to be supplied to the motor? Okay? This is power supplied by the motor. Okay? And there we go. We've got mechanical efficiency is P out over P in. To solve for P in, we say P out divided by mechanical efficiency, and we get 129. And this makes sense, right? Because P out can never be equal or more than P in. P in is always larger than P out because of mostly friction losses. Okay? All right, hope you're getting it.